Good morning and welcome to this week's CoE-MaSS seminar. Our speaker today is Dr. Ronalda Benjamin. She's a senior lecturer in the Mathematical Sciences Department at the University of Stellenbosch, where she obtained her PhD in 2016. She works in functional analysis and on B-Fredholm theory in ordered Banach algebras. She's also, very importantly, on the Functional Analysis Steering Committee, which coordinates functional analysis, the functional analysis community and activities in South Africa. And principal amongst those is the Piazza workshop, which was the workshop on functional analysis of operating group, and it is the meeting place of functional analysis in South Africa. We welcome Ronalda Benjamin. Thank you. And she will be talking on B-Fredholm theory in general Banach algebras.
Thank you very much, Bruce, and thank you also for the opportunity to give a talk in the CoE-MaSS seminar series. So the outline of my talk on B-Fredholm theory in general Banach algebras is as follows. So I'll start with some terminology and notations, and this is followed by a quick discussion on Dreisen invertible elements, which is very important in the study of B-Fredholm theory. So those who are not familiar with Banach algebras, let me start by defining this notion. So I'm interested in complex Banach algebras. So a complex vector space A is called a complex Banach algebra, or just a Banach algebra, if it is a unital algebra. So by unital algebra, I mean a complex vector space with a multiplication that is associative, left and right distributive. It's compatible with scalars, and there's this unique element which we call the unit of A and denote by 1A. This is also a Banach space for some norm. By a Banach space, I mean a complete norm space. And here I simply recall the notion of a norm space, which is also a metric space where we can talk about convergence of sequences. And as we know, complete means every Cauchy sequence in the space converges. And then finally, we require some relationship between the multiplication on the algebra and the norm on the Banach space, and that is that the norm of the product of two elements must be less than or equal to the product of the norms of the elements. So this is what we mean by a Banach algebra. Here are some examples of Banach algebras, the most obvious one being the complex plane with the usual multiplication and the norm given by the complex modulus. Another example is given by the vector space Ck of all continuous complex valued functions on a compact Hausdorff space K with pointwise multiplication and a subnorm. And we also have the algebra of all n by n matrices with complex entries. And more generally, the algebra of all bounded linear operators on a complex Banach space X. So just note on Lx, the multiplication you consider here is composition of operators. So here's some examples of Banach algebras. Next, I would want to introduce the notion of the spectrum of a Banach algebra element, which is defined in terms of the set of invertible elements of a unital algebra, let's say capital A, and which we denote by A minus 1. So let A be a Banach algebra. The spectrum of an element X, which we denote by sigma XA, and sometimes we drop the Banach algebra and simply write sigma X. This is given by the set of all complex lambda, such that lambda times the unit of A minus X is not invertible in A. We should clearly see that an element is invertible if and only if 0 does not belong to the spectrum of the element. It's important to note that the spectrum is a non-empty complex subset of the complex plane. And here I give some examples of the spectrum of a Banach algebra element. So if you consider n by n matrix, its spectrum is given by the set of all eigenvalues of the matrix. And if we consider a continuous function, f, then its spectrum is given by the range of the function. So from holomorphic functional calculus, we have the following. So if you consider a Banach algebra element X, and well, then a function f, which is holomorphic on an open set U, which contains the spectrum of X, give rise to a new Banach algebra element, which I give here, and I denote it by fx. Now, a question here is whether there's a relationship between the spectrum of X and the spectrum of this element fx. Indeed, there is. The spectrum of fx is simply f of the spectrum of x. So if you computed the spectrum of x, you can also offer the spectrum of f of x. Now, a spectrum, and in this talk, we will also consider other types of spectra that satisfies this identity is said to satisfy the spectrum mapping theorem. Okay, so over the years, various types of generalized inverses have been proposed and investigated by several authors. In this talk, I will focus on the Dresden inverse, which was introduced by Dresden in the 1950s. So let A be a unital algebra. An element X in A is said to be Dresden invertible if there exists an element Y that commutes with X. Y can be written as Y times X times Y. And X minus X times Y times X is nilpotent. So power of this element is equal to 0. So we will denote the set of Dresden invertible elements by AD. And it's clear that every invertible element is Dresden invertible. We can simply choose this Y to be the inverse of our X. This inclusion is strict in general. For instance, 0 is Dresden invertible, but of course not invertible. In general, any nilpotent element is Dresden invertible. We can simply choose this Y to be 0, but nilpotent elements are not invertible. I could also probably mention that if A is finite dimensional, then the set of Dresden invertible elements agrees with the whole of A. Okay. Also probably important, if such a Y exists, then it is unique, and we refer to it as the Dresden inverse of the element X. Okay, so if we replace the set of invertible elements in the spectrum of the set of Dresden invertible elements, then we set up what is called the Dresden spectrum of an element of a Banach algebra. So this is the set of all complex lambda, such that lambda times the unit minus X is not Dresden invertible. What we should know about this spectrum, the Dresden spectrum, it is also a compact subset of the complex plane, but the Dresden spectrum might be empty. So in view of this inclusion, we also see that the Dresden spectrum is contained in the spectrum. In this talk, the notion of a homomorphism will also be important. So a map between unital algebras, map T between unital algebras A and B is called a homomorphism if T is linear, T is multiplicative, and T sends the unit of A to the unit of B. So one can then very quickly establish that homomorphisms map invertible elements to invertible elements and Dresden invertible elements to Dresden invertible elements. And if we use this first inclusion, we see that for any element X on the domain of T, the spectrum of Tx is a subset of the spectrum of X. And if we use this inclusion over here, then the Dresden spectrum of Tx is a subset of the Dresden spectrum of X. And then just finally, we will denote the null space of homomorphism T by NT. So this is the set of all elements in the domain of T, which are mapped to 0. Now, well, the focus of my talk is Fredholm theory in general Banach algebras, but I would want to mention that Fredholm theory, as well as B-Fredholm theory, originated in the context of the boundary linear operators on a Banach space X, which I denote by Lx. So important class of operators that are studied in Fredholm theory are the Fredholm operators. And here I quickly point out the definition of a Fredholm operator. So these are operators whose range are closed in the null space, and the quotient of X modulo the range of the operator, they are finite dimensional. The theory of Fredholm operators was later generalized by Berkani, who introduced and studied B-Fredholm operators. I'm not giving the definition here, but what I want to point out as we continue studying these theories in general Banach algebras is the following well-known results. So by a well-known theorem of Atkinson, Fredholm operators are those operators whose quotient t plus fx, this is the finite rank operators on x, and this is invertible in this quotient algebra. And for the B-Fredholm operators, we have something similar, replacing invertible by Dreisen invertible. Now we can state this in terms of a homomorphism. So in red, we simply have that pi of t. Pi is the canonical map on Lx, which maps operator t to this, its coset, t plus fx. This is then invertible in this quotient algebra. And in the case of B-Fredholm elements or operators, we see that pi of t is Dreisen invertible in this particular algebra. So next, I'm simply going to replace this homomorphism here by an arbitrary homomorphism, and I will consider an arbitrary element in the domain of that homomorphism, and then I can set up the notions of Fredholm and B-Fredholm in the general setting of Banach algebras. In Fredholm theory, there are also notions of Weil and Brauder operators. This I will point out in the general setting of Banach algebras. So next, these are now natural generalizations of concepts that were introduced in Lx. So let's consider an arbitrary homomorphism. I'm removing bounded here. So Hart introduced these notions relative to a bounded homomorphism. Matun and Rovenheimer noticed that we don't need bounded. So I'm just going to remove this. So with respect to a homomorphism T between unital algebras A and B, we call an element X in the domain of T Fredholm if the image of X under T is invertible in B. An element is called Weil if it is the sum of an invertible element in A and an element in the null space of T, and Brauder if it is a commuting sum of an element in A minus 1 and an element in T. So you can write X as Y plus Z, Y is invertible, Z is in the null space, and Y and Z commute. Okay, so we will denote these sets of Fredholm, Weil, and Brauder elements by FT, WT, and BT. And so these inclusions now should follow easily. Invertible elements are Brauder because you can write an invertible element as x plus 0, because these commute. X is invertible, 0 is in the null space of any linear map, so this is a Brauder element. By definition, Brauder elements are Weil, and finally, Y is a Weil element Fredholm. If I take a Weil element, so you can write it as a sum of an invertible element and a null space element, I would want to look at T of the element. And before we pointed out that homomorphisms map invertible elements to invertible elements. So Weil elements are Fredholm. These inclusions are strict in general. So next, I'm simply going to replace these sets of invertible elements by Dreisen invertible elements to set up the objects that are studied in B-Fredholm theory, which is the focus of the talk. Okay, so again, we consider an arbitrary homomorphism between two unital algebras A and B. An element in the domain of T is called B-Fredholm if the image of the element under T is B Dreisen invertible. An element is B Weil if it is the sum of a Dreisen invertible element and a null space element, and B Brauder if it is the commuting sum of a Dreisen invertible element in A and a null space element. So here we will denote the sets of B-Fredholm, B-Weil, and B-Brauder elements by FTB, WTB, and BTB. And as before, these inclusions should follow easily. Dreisen invertible elements are B-Brauder, B-Brauder elements are B-Weil, and B-Weil elements are B-Fredholm. These are the inclusions we have in general. We also bring in the classes of elements studied in Fredholm theory. And all these inclusions are strict in general. Okay, so probably the first significant difference between the classes of elements from B-Fredholm theory and those from Fredholm theory can be seen as follows. So if I consider a null space element X, so Tx is 0 and therefore not invertible. So null space elements are not Fredholm and therefore they are not Weil and also not Browder. But null space elements are B-Browder because I can write the element as 0 plus X, which commute. 0 is Dreisen invertible. This is a null space element by assumption. So this is B-Browder and therefore B-Weil and B-Fredholm. So just confirm, well, this particular statement just confirms that these inclusions are strict in general. Another important property here is that the sets in blue are all closed under arbitrary scalar multiplication, while the sets in red are closed under non-zero scalar multiplication. For some more algebraic properties, so if you consider, in this case, we need these two sets to be Banach algebras. Probably forgot to point out before. So I only defined homomorphism between unital algebras. So once A and B are Banach algebras, then we talk about a Banach algebra homomorphism without assuming boundedness or continuity. So it just means that A and B are Banach algebras when we talk about a Banach algebra homomorphism. So in this case, and we have a commutative domain, then we actually see that the B-Weil elements, these will now coincide with B-Browder elements. They are closed under finite products as well as the B-Fredholm elements. When we drop the commutativity assumption, we see that these sets are closed under powers. This is what we get. I'm quickly recalling these inclusions from before. And interesting to note is the following. So if I consider a B-Browder element, which is not Browder, then that element will be B-Weil and not Weil. So that is the first inclusion. This is with respect to a Banach algebra homomorphism. And an element which is B-Weil and not Weil is going to be B-Fredholm and not Fredholm. So this is the inclusion over here. We do not have that an element which is Dreisen invertible and not invertible is going to be in general B-Browder and not Browder. Some of these elements can actually be Browder as well. So this is quite an interesting set of inclusions here. Yeah. So next, I would quickly want to point out some necessary and sufficient conditions for an element to be B-Fredholm. So if a Banach algebra homomorphism has the lifting property, so yeah, explain what lifting property means. So in general, homomorphisms will also map idempotents to idempotents. But once we have this identity, then this T is said to have the lifting property. Now, with respect to homomorphisms, Banach algebra homomorphisms with a lifting property, an element X is B-Fredholm if and only if there exists an idempotent P such that X plus P is Fredholm. These two elements over here belongs to the null space of T, and P times X times P is T nilpotent. Now, T nilpotent means that T of this element is nilpotent in B. So power of T of this element is 0. We observed that if we drop the lifting property, then the right to lift implication also holds. So you don't need lifting property in that case. And what we also noticed that without the lifting property, we actually have a left to right implication when we replace B-Fredholm by B-Weil. And this, the set of Fredholm elements is then replaced by the Weil elements. And also the same holds for when we replace the set by the B-Browder elements and the Fredholm elements by Browder elements. This result holds for with respect to arbitrary Banach algebra homomorphisms. Okay, so there are some interesting results, perturbation results involving the B-Fredholm, B-Weil, and B-Browder elements, but I'm not going to go into that. I would want to focus next on the spectra that we obtain from these classes of elements that I've considered. So again, we consider an arbitrary Banach algebra homomorphism in an element X in the domain of T. So before we defined spectrum in terms of the set of invertible elements, and then we defined Dreisen spectrum in terms of the set of Dreisen invertible elements. So I'm going to use the Fredholm elements now to set up the Fredholm spectrum. So the Fredholm spectrum of X is simply the set of all complex lambda, such that lambda times the unit minus X is not Fredholm. So one can actually show that the spectrum of the set coincides with the spectrum of Tx. So this is the usual spectrum now. The Weyl spectrum of X is a set of all complex lambda, such that lambda times the unit minus X is not Weyl. This set we denote by omega Tx. And then the Browder spectrum is where we replace Weyl by the set of Browder elements. And this set will be denoted by beta Tx. Okay, so if we recall the set of inclusions from before, then the following is true for the corresponding spectra. So the Fredholm spectrum is a subset of the Weyl spectrum. That's because Weyl elements are contained in the Fredholm elements. So if it is not Fredholm, it cannot be Weyl. The Weyl spectrum is a subset of the Browder spectrum, which is then a subset of the usual spectrum, or just the spectrum. Now, like the Fredholm spectrum, we can also express the Weyl and Browder spectrum in terms of just the spectrum. So the Weyl spectrum of an element is the intersection of the spectra of X plus Z, where Z is in the null space of T, and the Browder spectrum is the intersection of the spectra of X plus Z, where Z is in the null space of T and commutes with X. So from these, it should be clear that all these spectra are complex subsets of the complex plane. And since the spectrum is non-empty, these are all non-empty complex subsets of the complex plane. Of course, these inclusions are strict in general. Okay, so next I will set up the spectra that we study in B-Fredholm theory by considering the relevant sets. Again, we consider an arbitrary Banach algebra homomorphism T and an element X in the domain of T. And now we use the sets of B-Fredholm, B-Weyl, and B-Browder elements to set up new spectra. So the B-Fredholm spectrum of X, it's the set of all complex lambda, such that lambda times the unit minus X is not B-Fredholm. And here we can show that this set agrees with the Dreisen spectrum of Tx. So before, for the Fredholm spectrum, we have the spectrum of Tx. For the B-Fredholm spectrum, this is the Dreisen spectrum of Tx. Again, for the B-Weyl spectrum, we consider the B-Weyl elements. This set, the B-Weyl spectrum of an element will be noted by WTBX. And the Browder spectrum of X, which is the set of all complex lambda, such that lambda times the unit minus X is not B-Browder, this will be denoted by BTBX. Okay, so we're simply recalling the inclusions from before, and this is what we have now for the corresponding spectra. So the B-Fredholm spectrum is a subset of the B-Weyl spectrum, which is contained in the B-Browder spectrum, which is then a subset of the Dreisen spectrum of the element X. We can also express the B-Weyl and B-Browder spectra in terms of the Dreisen spectrum, as we've done for the B-Fredholm spectrum. In this case, we see that the B-Weyl spectrum is the intersection of the Dreisen spectra of X plus Z, where Z is in the null space, and the Browder spectrum, B-Browder spectrum of an element X is the intersection of the Dreisen spectrum of X plus Z. As before, Z is in the null space and commutes with X. Again, these inclusions are strict in general. And from these results, we see that all these spectra are now complex subsets of the complex plane, because we're taking intersection of complex sets in C. Since the Dreisen spectrum can be empty, the B-Fredholm, B-Weyl, and B-Browder spectra can also be empty. But they're all complex sets. So natural question now is whether these spectra satisfy the spectral mapping theorem. So let's quickly look at this next. So the question here is, if I consider a Banach algebra homomorphism T, an element in the domain of T, a function which is holomorphic on an open set containing the spectrum, what is the relationship between the B-Fredholm spectrum of Fx and the B-Fredholm spectrum of X? And the same question applies to the B-Weil spectrum of fx and f of the B-Weil spectrum of x. And here we consider the B-Browder spectrum. Now, before I point out these results, we can quickly recall what is familiar to us for the spectra coming from Fredholm theory. So Hart in his 1982 paper proved the following. So on the additional assumption that this F is also non-constant on its component of U, the Fredholm spectrum satisfies the spectrum mapping theorem, but the Weil and Browder spectra only satisfy one-way spectrum mapping theorem. Now, I think in 2001, Berkani proved that the set of Dreisen invertible elements forms a regularity. Now, by regularity, I mean the following. So a non-empty subset R of a Banach algebra, let's say capital A, is said to be a regularity if the following two properties are satisfied. So if x in A in N, and natural number, positive integer, x is in R if and only if x to the N is in R, and if x and y are relatively prime, then x and y in R if and only if x times y is in R. So the set of Dreisen invertible elements is an example of a regularity. Miller then later on split the axioms of regularity into two parts, where he studied upper semi-regularities and lower semi-regularities. I'm only going to mention what upper semi-regularity is for the purpose of this talk. So when we replace regularity, by upper semi-regularity, then we have a set that satisfies the in 1 and 2 the left to right implications. So that is upper semi-regularity, and we also require that the set contains a neighborhood of 1. That's also important. At the end, one will be able to show that a set is a regularity if and only if it is a lower and semi-regularity. So why are these important? So via regularity theory, we can also get to spectrum mapping theorems. For instance, if R is a regularity, then if you look at the set of all complex lambda, such that lambda times the unit minus x is not in the regularity, this set will satisfy the spectrum mapping theorem. So if I denote the set by, let's say, sigma Rx, then we have that sigma R of fx is equal to f sigma Rx. So once you know that the set is a regularity, you can conclude a spectrum mapping theorem for the spectra that you obtain from that set. So what we know now is that the Dreisen spectrum satisfies the spectrum mapping theorem because the set of Dreisen invertible elements is a regularity. And if one uses that fact, you can also show that the set of B-Fredholm elements form a regularity. And that, of course, implies that the B-Fredholm spectrum will also satisfy the spectrum mapping theorem. So what do we know about the B-Weil and B-Browder elements? So we could only show that if the domain of Banach algebra homomorphism is commutative, then these, well, in this case, B-Weil and B-Browder elements, these sets coincide, and then we will get an upper semi-regularity. So I don't know if this is still true if we drop commutativity, but since we have an upper semi-regularity, this is what we can say in general. So regularity, we have a spectrum mapping theorem for this set. If we have an upper semi-regularity, which contains the set of invertible elements, then we only have an inclusion over here. So this is results by Miller. So if I go back to that previous slide, so the set of B-Fredholm elements form a regularity. So we have an identity over here. This, the B-Fredholm spectrum satisfies the spectrum mapping theorem. And since we could prove that the sets of B-Weil, B-Browder elements form an upper semi-regularity with respect to Banach algebra homomorphisms with commutative domains, we can only give a one-way spectrum mapping theorem for these spectra, but we need commutativity. Like I said, I don't know if this is still true, if we drop the commutativity assumption. So next, I would want to focus on the connected hulls of the spectra that we considered in this talk. So if we have a complex subset, let's say K of the complex plane, then we can talk about its connected hull, which we denote by eta K. So what is the connected hull of K? This is simply the complement of the unique unbounded component of K. So I give you a complex set, so a closed and bounded set. It might have some holes, but there will be a unique unbounded component. And if you consider the complement of that unbounded component, you obtain the connected hull. So if you want to picture this, it's basically the set, and then you fill the holes of the set, something like that. So the following properties should now follow easily. So any set, of course, is contained in its connected hull. If I consider a complex set, and I look at its connected hull, then the connected hull of the set will simply be the connected hull of the set. And for any two complex sets, K1 and K2, where K1 is contained in K2, the connected hull of K1 will be contained in the connected hull of K2. Okay, so I'm recalling here the spectra from Fredholm theory. So this is the Fredholm spectrum, Weil and Browder spectra, and that's the usual spectrum of the spectrum. So though these sets do not coincide in general, what the authors of this paper showed is that when the homomorphism has the Ries property, then these sets will be the same. So just quickly, what do I mean by strong Ries property? So homomorphism, Banach algebra homomorphism has the strong Ries property if for each element in the domain of the homomorphism, the accumulation points of the spectrum of X belong to the connected hull of the Fredholm spectrum of X. An example here of homomorphism with the strong Ries property is given by the canonical map on Lx, which maps a operator to its coset T plus Kx, where Kx is a or Kx denotes the ideal of compact operators. So this result over here is actually a generalization of a result for operators. Yeah, this is due to Hart and the author over here. So natural question now is whether we can replace the Fredholm, Weil, and Browder spectra by the B-Fredholm, B-Weil, and B-Browder spectra. So this is the question. If T has the strong Ries property, do we have that the connected hulls of the B-Fredholm, B-Weil, and B-Browder spectra coincide for all elements in the domain of T? Now, this is still an open question. We could demonstrate that if T does not have the strong Ries property, then these sets are not in general the same. And we could also prove the following. So if T has the strong Ries property and B is commutative in semi-simple, we can actually replace this with something weaker, but then I'll have to explain some terminology, which I don't want to do. But if B is commutative in semi-simple, then the connected hulls of, this should be B-Fredholm, B-Weil, and B-Browder. So just bring that down. So these will agree, but this is for all elements in the domain of T whose Fredholm spectra contain no isolated points. So this part was important to set up the following property. So if you take an element which is Drazen invertible and B-Fredholm, then that element is going to be B. Let me just quickly check. B, Drazen invertible, and B-Fredholm ends up being B-Browder. I think that's it. And it's something that we needed to get to these identities. Again, I do not know if this is true for all elements in the domain of an arbitrary homomorphism with a strong Ries property. I think I might have gone a bit too fast, but this is actually where I would want to end. So if there are any questions, you are welcome to ask. But I will conclude with the fact that this is still an open problem. Yeah, so thank you very much for listening.
Thank you, Ronalda, for a very interesting talk. Do we have questions from the audience? Well, I have one or two questions.
Okay.
Have you built any concrete examples of your different operators and worked out their different spectra? For instance, on
Can you maybe move closer to, I believe, the laptop or somewhere, then I can hear you.
this way.
Yeah, much better.
Now can you hear me, Ronalda?
Yes, yes.
Have you worked out any concrete examples on, let's say, little LP spaces, the operators on little LP spaces or something like that, of these different setup operators there, and worked out the spectra and things like that for these different operators? I know it would be a painful task, but
definitely.
it might be interesting to actually see the differences. See when you try and do some hands-on concrete
yeah. Many of the examples, and also dealing with operators on, I believe, particularly focusing on L2, all our examples suggest that we should get to these identities. But again, coming up with a proof is something different. But all our examples seems to indicate that this could be true. Yeah, but some work is still needed there.
The L2 case is very, very special and very nice.
Yeah.
If you take it just to something like an L1 or case or something like that, where you've got the maps from L1 to L1, the bounded maps of that, you might get some interesting and weird examples. So you've moved away from your underlying space being a Hilbert space into something which distinctly Banach, not Hilbert. But it was just, I wondered whether you tried to actually do any of those.
I need to do more.
Some good coffee and some time.
Sure.
And have you actually looked at the Fredholm theory is used all over in relation to differential operators. And well, the problem with differential operators is they're unbounded. But now when you work with the resolvent operators, and now you can start building a theory, because now your resolvent operator is a bounded operator, and then you can start working with the Fredholm type theory that relates to bounded operators. So that's the way you get around that. Have you looked at any of the connections of what you do in B-Fredholm theory with differential operator theory? With on LP?
No, I have not, but definitely considered that. I'm actually new to B-Fredholm theory, and I'm, still much to learn, but I will make a note of that, and it's something to explore. Thank you.
As soon as you step outside the underlying Hilbert space structure, you have to work a lot harder, as I'm sure you discovered with what you're doing.
Yeah, that's also why you stay away. But yeah, no, it's worth looking into. Thank you.
But there's a question online.
Hello, Sana.
Hello, Ronalda. Thank you. Thank you for a nice talk.
Okay.
I have a few questions. Let me see. So, I mean, I think what Bruce says is very true. It's nice to have some good examples, but as you'll easily find out, actually doing spectral theory for operators. When you look at concrete operators, it's not always that easy. I think Yeah, one question maybe. So, I mean, the standard example that you have is say Banach operators on the Banach space, and then you do a quotient map. But are there other kind of maps that you can do, which would give you like something interesting, other than doing a quotient to um, finite rank operators or compact operators, etc.?
Is it still focusing on operators or any other Banach algebras that you can consider?
Well, other examples too, but even if you say you look at operators on the Banach space, but now you look for a different map into another, yeah, but other examples are also fine.
Yeah. So so we would establish our results, of course, in a general setting, and then we would apply it to various examples. I myself have not started with an example where we don't consider the canonical map and see what is happening there. So I think, yeah, I can look into that. But mostly when we set up this result, we immediately apply it to that particular case where things kind of started, yeah. But whatever we set up, it would apply to any Banach algebra homomorphism. It would just be nice to give some more examples of it. Yeah.
I mean, yeah, it's nice to have very general setup and nice results.
Yeah.
You would also need some good examples to see why you want to do this. The other thing I've asked you that before, I think, but I mean, if you look specifically at the example with Fredholm operators, and you you take the quotient map and then they become the invertible operators. When you do this, I mean, information that you lose, for instance, I think is the Fredholm index. Is there a way to sort of recover that? I mean, once you do sort of this quotient map, you don't see anymore what the original Fredholm index was, or did I miss that?
I'm just coming back to the slide where we pointed out these operator theoretic definitions. So when we bring the index, we can then set up notions like while operators where the index is 0. I didn't point out any of these definitions. I only jumped to the general setting to point them out. But a while operator, for instance, would be a Fredholm operator with index 0. We can also set up Browder, but then we use ascent and descent. That's very operator theoretic. I didn't want to stay there. But quickly repeat your question. Once we have a Fredholm operator, we can talk about its index. And when the index is 0, then we have a while operator. That is.
I understand, but I mean, once you do this quotient map, then all the Fredholm operators are just correspond to the invertible operators, but you don't have a notion of index anymore, right? After you do this quotient map, right? So then you don't really distinguish anymore between indices, because everything is invertible, right? You cannot say, well, it's but it is true that if you look, I mean, if you look at sort of operators which are mapped into the same equivalence class, they will have the same index. But there's not a way to sort of recover the index once you did the quotient map, right? Or at least I don't know.
Yeah, I think taking the quotient will destroy the index. Destroy your access to it.
Okay.
Thank you, Sana.
Okay. Are there any further questions? Then I would like to thank Ronalda again for an interesting talk, and also to wish her well in her endeavors in studying B-Fredholm operators. I think there's some hard work in there that's been done and still to progress it to do.
Definitely.
We wish you well, and thank you for your talk.
Thank you very much, Bruce.